Okay, let's move on and deal with two specific techniques. The first one is referred to as centrography, and it's really a very old technique, and statisticians don't mention it too much. If you look at spatial statistics books that deal with point patterns, you won't see any mention of this. If you look at more geography text or planning text, the centrography thing is actually quite popular because it's very intuitive and it's very easy. It summarizes the pattern of the points. And it summarizes them in a different way from the intensity that we saw. The intensity had to do with how many points per area. Now let's focus just simply on the locations. And think of a concept that is like the average location. What is a point that represents the pattern on average? And that is a very simple notion. You take the average of the x-coordinates, you take the average of the y-coordinates, whatever that turns out to be, that is your mean center or central point. Very easy to compute. And it's straightforward to extend that and use a median. So you take the median of the x's and the median of the y's, that is a median center. These two are very simple summaries of the point patterns, of the locations of the points. You can get a little more sophisticated and say, try to find the center of gravity, the point that has the shortest overall distance to reach all the points. Of course, distance in straight line. If you do this on a network, that's a different story. That's quite a bit more complicated. But in straight lines, it's not really that complicated. And then you can map those things. That's why it's so intuitive. Now, for now, ignore the ellipse and just look at the cross. That cross is the mean center. So that's the location that summarizes, if you wish, gets the average of the horizontal directions and the average of the vertical directions in the pattern. And just to, the median and the mean are, and the shortest travel distance are all in the center of this point pattern, and you can't really see it. But, I mean, you can't really see that well either, but it's great on my screen. They're very close together. Now, this isn't always the case. And when will it not be the case? Outliers. Yeah. The median is much less sensitive to outliers than the mean is. Just like we saw in the box plot the other day, when the mean and the median are different, it points to the effect of the tails. Because the tails work on the mean more than they do on the median. So when you see major differences between these three locations, that points to outliers. Now, what are the outliers in this context? They're outliers in terms of x, y coordinates. So they're points that are away from the central pattern of the other points. So they either have a very high x, which means that they're way out east or way out west, or a very high or low y, meaning they're way out north. And so you could have a situation where you have a bunch of points in the middle and then one really far south or one really far north. Then the mean could actually be a point that moves out of the central blob of points if the effect of the outlier is large enough, where that would never happen with the mean. The second concept is to focus on the second moment. First moment is the mean. Second moment is the variance or the standard deviation. And so you can have a thing which I haven't shown you here because it's not that interesting. You have what's called a standard circle, which is essentially a circle with the radius equal to the standard deviation of the points, of the distances to the center. So it just gives you a sense of how compact or spread out the point pattern is. So you could have 2 point patterns with the same mean central point, but one is right around the mean, is more compact than the other. These circles would show you that. A more subtle descriptor is the so-called standard deviational ellipse, which is similar in notion, but it allows 2 different axes. So an ellipse is like a circle that's been stretched, right? So you have 2 axes in the ellipse, a main, major, and a minor axis. Along each of these, they are centered on the mean center. So they're centered on the average of the x and the average of the y. And then in each of these directions, you have a standard deviation. And you draw the ellipse so that the endpoints on the axes correspond to 1 or 2 standard deviations. It doesn't matter which one you take, as long as you take the same for both axes. So then the ellipse gives you a sense of how uniform the pattern is, as opposed to showing directional elongated effects. So if all the points are spread more or less uniformly around the center, then we would have a circle. If there is some concentration in a particular direction, then we get more of an ellipse form. If it's pronounced, like we have kind of a thin pattern, then the ellipse really gets stretched out. So the standard deviational ellipse gives you a sense of this patterning around the center, how uniform that is, or whether there are directional effects. In addition to these 2 axes, you also have, this is a little more subtle, an angle between the axes. And if you want to read up on this, there is a reference in the summary that gives you step by step how this is computed. I don't want to spend too much time on it because it's really only a very crude descriptive device. It's useful as a quick and dirty way of looking at the point pattern, but it's really not of any help in terms of suggesting what the process might be or helping us in estimating that process for that matter. So why would we use it? As I said, it's a quick and dirty look. It's a visual summary of the pattern. It shows us, especially in a comparative sense, whether the core of the pattern has shifted, whether the, if you wish, the distribution around the core has shifted. So one setting where this could be used is say, continuous monitoring of events. For example, 911 calls. You get 911 calls coming in, you know where they come from, you have the location of the call. So every day you could make a map with the points of where the 911 calls came from. You get the central location, draw the ellipse around it. So then you can see whether these ellipses are more or less constant or move around in space. You can do this for a number of different phenomena. You can look at crime, you could look at accidents, you could look at bird sightings, you know, whether the birds are all in the same location or they're moving over space. This is primarily what these centrography tools are used for. They give you a sense of both the compactness as well as any kind of directional pattern in the data. And just to illustrate this with our Buffalo data, it's very straightforward. We have the, I split the pattern in the pre-95 and post-95 period, so cut it in half and say we're interested in finding out is the patterning in the first half of the decade the same or different from the patterning in the second half. And you know, what can you say? Not much. Okay, you see that there is some kind of a shift, seems to be in the northwest direction, but slight. And the shapes of the ellipses don't seem to be very different between the 2 periods. So this would suggest that these patterns have not changed very much. It would be totally different if, for example, for one period, you would see all the points here, and then for another period they would be all here. That would suggest a major structural shift. I mean, if you look at these points, these are all the points for the 10-year period. you don't know when this happens. You could look at this year by year and see if there's any kind of change in the patterning, and an initial look at this is just cut it in 2 periods and see if there's any difference. And from this, you wouldn't see any difference. So in the lab on Thursday, we'll do this centrography exercise. This is very popular with police analysts and crime analysts to have a very quick view of central patterning of events. You know, these could be drug busts, they could be accidents, car accidents, they could be vehicle thefts. You know, you want to get a sense of how patterned this is and if this pattern changes over time, or after a particular intervention is made, does the pattern change? You know, you make a series of arrests in a particular part of the city, does everybody just pick up and move somewhere else and start over, or is it finished? Those are the kinds of applications. In the crime stat manual, one of the readings is a chapter that deals with these kinds of summaries, and the latest, the third version of crime stat manual has several vignettes in the manual, which is like one-pagers that people write up with particular examples of applications of these techniques. So if you're interested in that, I would encourage you to take a look at some of these, because it gives you a sense of how this is used in real life. And they're not all crime examples. There are other examples as well. So this is centrography. It's pretty straightforward descriptive technique. The second technique I want to spend a little bit of time on today is quite a bit more complex. It is kernel density estimation, which is an approach to get a sense of the heterogeneity of the process. See, so far we've focused mostly on the homogeneity of the process. We've estimated this intensity as an overall average. We've computed this mean center as an overall average and the standard deviational ellipse. But now we're shifting our focus, shifting our attention to a little more realistic situation, is where we admit that the intensity might not be uniform, might change with location. In other words, in certain parts of the city, we have more homicides per square kilometer than in other parts of the city. This is symbolized by expressing, the intensity, the lambda, as a function of S, where S is a generic symbol for location. So typically S will be at least X and Y, you know, 2 coordinates. But it could be in 3D and so on, as I mentioned earlier on. The bottom line here is that we're allowing what we call spatial heterogeneity. Lambda S varies with location, rather than lambda S being the same lambda, the same intensity, no matter where we are. Once we allow the lambda S to vary with location, we have to figure out how does it vary with location. In the first instance, we want to describe this variation with location. And you can think of this as the same problem as trying to describe the distribution of a random variable. How do you summarize the distribution of the oil prices, the daily oil prices, or the stock prices of a particular stock? You know it goes up and down. There is some central tendency. There is a spread around this central tendency, but you can do better than that. That's just 2 numbers that try to summarize the whole distribution. So one thing you could say is, I'm assuming that it follows a normal or Gaussian distribution. So then, once I have the mean and the standard error, standard deviation, I'm in business. I can completely characterize this distribution. I plug this into my nice formula for the normal distribution, and I get my nice bell shape, which tells me everything there is to know about the distribution of that variable. Here it's not that simple because we don't have, or at least not yet, a counterpart of this nice Gaussian assumption. And instead of assuming a distribution, we're going to try to let the data tell us what the distribution might be. Okay. Step back a second, and you have your stock prices. I give you 100 observations on the price of your favorite stock. Okay. And I tell you, no assumptions. How would you try to summarize and describe that distribution? We've already seen it. We saw it last week. One of the tools that we looked at last week does exactly that. Which one? Well, actually two. Box plot and a histogram. What does the histogram tell us? It tells us how many observations in different intervals of the data. So we had to pick intervals. We picked 5 or 6. What if we increase the number of segments and make the intervals smaller and smaller and smaller? What do we get? A smooth curve, a density. Now, what happens when you make these intervals narrower and narrower? You have fewer and fewer points in them. So it doesn't work. I mean, it works conceptually. It doesn't work in practice. The solution is not to just take those points in the interval, but to take more. And to borrow strength, as Bayesians like to say, from the information in the neighboring intervals. And this is exactly what a kernel density estimator does. It's a non-parametric way to estimate a density function by not just taking individual points or small intervals, but by borrowing information from neighboring locations and weighting them. Before we get into the specifics of the kernel estimation, there's a subtle difference here which is confusing because not everybody is careful in referring to this. And in the point pattern literature, there is actually a difference between intensity and density. Intensity is what we talked about earlier, the average number of events per unit area. And we'll formalize this more next week, but conceptually, we're thinking of this unit area becoming smaller and smaller and smaller and smaller. So conceptually, we're looking at the limit of the number of points in an infinitely small area. Now, you know, from a practical point of view, if your area is too small, there's not going to be anything there, right? But it's a mathematical tool to approximate the continuity of the phenomenon. And so if we're looking at the number of events, and we try to fit the surface of the expected number of events, we'll call it intensity. If we standardize it, and it becomes a probability, then we call it a density. So probability is what we are more comfortable with, maybe, is that it gives you this density function, gives you the probability of getting an event at any particular location. So that's really something we can later use to simulate. Because we could draw a random number at each location, compare its outcome to what we get in the density function, and then depending whether it's above it or below it, we get the event or we don't get the event. And so we can simulate patterns using this type of device. The bottom line is these two are connected, obviously, because the one is the average number of events, the other one is the probability of event. If you divide the average number of events by the total number of events, you get the density. So the two are connected just by a scaling factor. So their spatial pattern will be the same. If you draw contour lines for an intensity function, or you draw contour lines for a density function of the same point pattern, they will be identical. The values associated with the contours will not. One will be related directly to the number of events. The other one will be related to a probability. So it will be between 0 and 1. It's important to know this because some software is not careful in calling it intensity or density. And then you get these weird numbers. You know, you can't have a probability that is 5. Right? If you see that, then it's an intensity function. If it's a fraction between 0 and 1, then it's a density function. But for practical purposes, if you're making maps or contour lines or 3D visualizations of these surfaces, they will be the same. They're just rescaled by a constant value. Okay, back to the kernel estimation then. We're letting the data determine the distribution. You think of the histogram, we make our intervals, we count how many observations are in each of the intervals, we draw our little boxes, we have a sense of the distribution. We want to make that smoother. By making it smoother, we're going to, as I said, borrow strength from the neighbors and make some kind of a weighted moving average of what we observe in a certain interval. You can think of a kernel as being an interval that you put over the data. Think of equal distances, and at each distance you put some kind of tent over the data, and you give more weight to points, to locations that are closer to the center than further away. So that is formalized in this expression here, where you have a function at any location. So this can be computed for any location. And in practice, what you do in 2 dimensions, you have a grid. And you compute this kernel function at the points on the grid. It's very important, and later we'll get back to this when we develop statistics for point patterns, to make a distinction between the points on the grid, those are the U's, and the actual point events, those are the UIs. Now sometimes, and you'll see it in the next slide, this is discussed in the context of putting the tent, so to speak, centered on the UIs, but it doesn't have to be. It could be centered anywhere, because you're really not estimating something only for the observation points. You're estimating it everywhere. It's an intensity function, it's a density function, so you need probabilities even for those locations where you don't observe an event. Remember, our mapped pattern, we only see what happens. We don't see what didn't happen. Here we're trying to get a handle on what didn't happen by modeling the probability that an event might occur. Now, this is separate from the event that actually did occur. We use the information from the events that did occur to say something about where they might have occurred. So formally, we have any location U, we have location of our events U of I. K is this magic kernel function that I haven't talked about yet. B is a bandwidth. B is the size of the tent. Is how far away you're willing to go, because this is a summation over all the I. Now, because of the particular shape of the K function, not all the I's will be counted. In fact, they will be discounted. As they are further away, they get smaller and smaller weight. And in fact, beyond the given distance, for most kernel functions, they get no weight at all. So they don't get counted. And that is determined by this B parameter, which is more important than the actual functional form of the kernel, as it turns out. And I'll show you in a second an example. And then this NB is a scaling factor. B has to do with the bandwidth. If you take more points into account, you have to scale down more to get a proper density or a proper intensity. and the n has to do with the overall number of points. So in practice, what this means is we're going to count how many points are within a given distance from where I am, but then they don't get counted equally. So you might say, okay, I'm putting my peg here, I'm looking 5 meters this way and 5 meters that way, how many points do I have? Say I have 2 on this side and 1 on that side, you might say my value is 3. It's not, because these points are not equal distances from me. So the ones that are furthest get a small weight, say 0.2. The ones that are closest get 0.8. So then we add these all up, and we rescale it, and out comes this f of u. And we move our peg to another position, do the same thing. So in pictures then, you better look at your screen. Yes?
So, in that function, and get back to the mass, right? So what's the possible value of u and ui? Is it relative perturbation or is it the coordinate?
Well, on a line, it's just a position. In 2 dimensions, it's the coordinates of the two. So, but they're just indices, right? What you're really doing, and I'll show you in a second, is you have a circle, and you're counting the points, but you're taking the distances of the points into account. Those distances, that's this. See, this is the distance between u and ui, rescaled by the bandwidth to make it a number between 0 and 1. That number goes into this function. And then out of that comes something that is related to f. So the function transforms these distances into a value. And in this example, the function is a normal distribution. And this is pulled out of the crime stat manual. You can't see it very well, but this is like a bell shape centered on this particular point. And one way of thinking about this is of centering all these bell shapes on these points and adding them up. And then out comes this function that is a kernel function. That's one way of thinking about it. I like to think about it differently, where you actually put your pegs, say, at 2, 3, 4, 5, 6. At each of these, you would put your bell shape, and then you would count the points that are under the bell shape. In fact, if you do that, if you add them all up, then this is what you get. And then, of course, you can rescale this to get a probability. In other words, to make sure that the area under the curve sums to 1, is exactly 1. The total probability equals 1. It has to be that way. What's very important here is how wide this bell shape is. So if we make it spikier, narrower, this is the kernel that results for the same data. So this is a lot spikier. Very important, the crucial role of the bandwidth in getting your pattern. The rule of thumb is simple. The shorter the bandwidth, the spikier. The larger the bandwidth, the smoother. Okay. What is the extreme? When you take your bandwidth so large that all the points are included for each location that you consider. What will your kernel look like in that case? Flat. And it will be equal to the intensity, to the average number of points per areal unit. Or it will be a uniform probability. The probability of having an event is the same everywhere in space. So one way of thinking about this kernel is as some kind of smoothing device. In the extreme, when you take all the points into account, is just simply fat. As you start weighting them differentially, it starts taking on a different shape. The fewer points you take into account, the more each individual location will determine the shape of the kernel, meaning it will be very spiky. The wider your bandwidth, the more you have some kind of averaging or smoothing, and The crucial decision here is not to do too much of either. If you make it too spiky, you don't have any information because there's no generalization. You get all the individual points back. If you make it too smooth, there's also a lot of information because the heterogeneity has been moved up, has been smoothed out. So you have to be in between somehow. And I don't really have time to get into technical details too much, but there are several theoretical findings and mathematical derivations that give you an optimal bandwidth for particular situations. And one thing you can do always is experiment. You can always, in an exploratory fashion, change the bandwidth and see if this changes the spikes that you find in the distribution or the dips that you might find in the distribution. Now let's get a little more formal. What is this kernel function really? This k. Remember, the u minus ui over b goes into k. U minus ui is the distance, in our application, is the distance between our reference point u and the data points u at I. So we're taking this distance from our reference point to all the data points I, in principle. Right? But then it goes into this kernel function, so for all practical purposes, we eliminate a bunch, the ones that are too far, the ones that are beyond the bandwidth. The function itself, because it has such a connection to a density function, has to be positive, has to integrate to 1, and is typically symmetric as well. Now, in the case of spatial data points, it's actually pretty easy because these are circles. You can think of them as a disk moving over the points, and then the points that are inside the disk gets moved into this k function and somehow transformed into a value, the density. The bandwidth determines how many points are included. There are two ways in which we can use the bandwidth. We can set it fixed, once and for all, 10 meters, no matter where we are, or you can change the bandwidth. And that's actually the preferred approach, and that's called an adaptive bandwidth, where we make sure that we have enough points to compute our kernel estimate. I mean, think of the Buffalo data set, if you can imagine it, and if you're in the lower left corner, there's nothing there. So if we put a disk on there with a given radius, there's nothing in there. So we get 0. Should we get 0? We should get 0 if there truly is no probability of an event happening there. But just because nothing happened there doesn't mean it's not possible that something might happen there. So in those cases, we don't want 0. I mean, there's not going to be a high number, but we want something. In order to accomplish that, we adjust the size of the radius to make sure that we have a minimum number of points. Let's say at least 5 points or at least 20 points. That's an adaptive kernel. So in the denser parts of the sample, we'll have a narrower kernel. We'll have a spikier pattern, which is exactly what we want, to capture the heterogeneity. In the parts that are very sparse, where there aren't very many points, we'll have a smoother pattern because we want to get the information from the points that are a little further away to get something other than 0. 0 is not good. 0 is only good if it is truly 0, and we want to be very wary of this because we don't really know what didn't happen, right? And that is the key here. We want to get a sense of the probability that something would happen. It's not because no murders happened in a month that it's impossible that a murder happens in ever. Right? Think of this in a spatial context, and it's not because a murder didn't happen in that particular neighborhood that it's impossible that murders happen in that neighborhood. Right? It's the same with accidents. It's not because you haven't had any accidents that means that you can't have any accidents. You've just been lucky. It's the same thing. So mathematically then, we need to say something about this k more specifically. So far we just said has to be positive, has to integrate nicely, has to be symmetric. We pointed to the role of the bandwidth. Now we have specific mathematical functions. One trick which we use in these mathematical functions is that we use z, which is the difference between our reference point u and our data point ui divided by the bandwidth. Now, say our bandwidth is 10 meters, just to keep it simple. And if we see something, a point 1 meter from our reference point, so then the z becomes 0.1. And 0.1 goes into this function. If we perceive something that's further away, say 20 meters, then we would have 2 as a value. For a lot of kernels, that's not allowed. And a kernel stops when z exceeds 1. This I of z less or equal than 1 is called an indicator function. That's a function that takes a value of 1 when the condition, in parentheses, is true, and 0 otherwise. Think of our bandwidth. What is the condition? The condition is the ratio of the distance between the reference point and the observed point to the bandwidth. In other words, if the point is within the bandwidth, this ratio will be less than 1, and our indicator function will say yes, 1. If the point is outside the bandwidth, our ratio will be larger than 1, and the indicator function will say no, 0, and it does not get counted. And then how it gets counted depends on this particular function. This is the actual k. This is some rescaling which has the b in it, and then 1 minus z, that's a triangle, just a straight going down. So the weights go down linearly as you move away from the reference point. The quartic or bi-weight is nonlinear, and it is more like a tent, where the weights decrease non-linearly as you move away from the reference point. Both of these have cutoffs. This one, the quartic, is by far the most popular. The Gaussian one, or the normal one, is different because the bell shape is infinite. So every point gets a weight. But of course, the points that are far away get very tiny weights. And for all practical purposes, they're excluded as well. But where is this important? It's important when you don't want to get 0. And we'll see an example of this in a minute. You don't like to divide by 0. Most people don't. So you don't want to get something that gives you a 0, that might give you a 0. Like one of these, a triangle or a quartic kernel might give you 0. Whereas the Gaussian one will not give you 0. It might give you very small numbers, but it won't be 0. So that's an important thing to keep in mind whenever you do ratios of kernel functions, for example. So the Gaussian, the triangle, and the quartic are the ones that you will see the most in the literature. You don't actually have to worry about this. The software computes it for you. And in practice, as I mentioned, how this works is you set up a grid system, and then at each point of the grid, think of this as a moving disk. You have the disk that computes the distances to the points within the disk. These become fractions of 1. These fractions go into this function, and they get added up, and then averaged or rescaled to give the actual intensity or density function. And then you move the disk to the next point on the grid, compute it again. And so this gives you, for each point on the grid, a value of the kernel function, and then you do use some visualization software to either show this as contour plots or as a 3D surface or some other fancy way on the map. Here we go. This is, and this is on purpose, the first time I did this, I didn't use a Gaussian kernel, and then I paid for it, and you'll see in a minute when I paid for it, of course, at the end, so I had to start over. A Gaussian kernel takes all the points into account. This is the Lancashire example because I'm interested in comparing the patterning for the cases to the patterning of the controls, the population at risk. I believe this is some kind of larynx cancer, and then the controls is a random subset of postcode addresses of the population. There's you can read up on it in the readings, there's a long explanation. It's a classic data set. Everybody, what happens in this literature is when people develop new statistical methods, they always apply them to these classic data sets because it makes it easier to compare the results to what other studies have done. It's like a benchmark, if you wish. So you'll see these Lansing Wood data set over and over, this Lancashire cancer over and over. There's a bunch of others that are classic data sets that are used over and over in the literature. Now, what we see here is a very weird pattern. Dark is high. What do you think is going on here with this kernel? It's a very strange pattern. It's actually not concentrated here. There aren't any points here. But the points are very nicely circular around them. So that's what the kernel picks up, is kind of this smooth pattern of points in a circular fashion. Then if we look at the controls, this makes a lot more sense. These get the high intensity as the darker colors of the controls. Now what we're interested in is taking the ratio of the cases over the controls as a measure of relative risk. And this is called the kernel density ratio, and this is where I got in trouble because we're dividing at each of these reference points, at each location F, we're dividing the kernel value for F, for the cases, by the kernel value for the controls. So if our kernel, which the quartic kernel does, gives us 0 for the controls, we divide non-zero by 0, or even better, we divide 0 by 0, which computers really love. So this thing doesn't work in this particular pattern with a kernel that has a real cutoff. But with the Gaussian kernel, you kind of finesse yourself around it because the Gaussian never gets really 0. It gets very small, but never really 0. So it does work. And what you're looking for is peaks in this distribution. If the null hypothesis, and we'll quantify this more next week and later, the null hypothesis is that these two show the same pattern, then their ratio should be 1. But if there are places where there's higher concentration of cases than there are of controls, then the ratio will be larger than 1 and will show a peak in the kernel, if you visualize the kernel ratio. There is a formal test, and I just want to mention it. We'll talk about this more formally later, which takes the log of this relative risk. And practical problems occur when the pattern is sparse, especially if you get a G of 0. And this is the ratio of these kernels, which now is very interesting. It tells you that there is relatively higher relative risks at the outskirts of this pattern and not in the middle. And this has to be put into context. I believe it's just about there that this incinerator was. I don't remember whether this was significant or not. I do know that for some tests it was and for others it wasn't. But this is a way in which you can compare two patterns. You could, for example, look at the pattern of vehicle thefts and regular burglaries. And you might be interested in finding out, is this the same or is it different? So you take your points from the newspaper, from the News Gazette, you take your burglaries, you take your vehicle thefts, you get their coordinates, fit a kernel density or intensity for one, kernel density for the other, take the ratio of the two, and look for spikes. Look for places where one is really different from the other. Or look at the difference between the two. That's another test, as we'll see later on. So what I tried to do today is just give you a sense of what point pattern analysis is about, the different kinds of data sets, if you wish, so simple patterns or marked patterns or multi-type or case control that you can encounter, and then start pushing a little bit towards formally assessing what this pattern is, either by means of simple descriptive devices like a mean center or standard deviational ellipse, or by means of a non-parametric device that lets you get at the whole continuous distribution of the point pattern by fitting this kernel to the points. One thing to remember about kernels, bandwidth is everything. The actual functional form doesn't matter that much. I mean, it matters if you want to avoid 0, but in terms of the overall patterns, it doesn't matter that much. And in the lab, if we have time, or if you have time, we can experiment with different kernel functions and then look at the maps, and then you'll see they're not actually that different. There is a difference between the normal and the other ones, but between the other ones, it's not that big a difference. Okay, next week we'll move into some of the more formal concepts and some formal test statistics dealing with point patterns. Okay, any questions? Yeah.
Okay, about the disks on the space, how all the areas are included? How is it done?
How is it done? Well, you basically make a grid. And let's say our points are here. So we go on the grid, and let's say we position ourselves here, we take the circle. And so the points that matter are these three. We take these distances, we divide them by the bandwidth, so gives you a fraction. Stick that in our function. Out comes a number. That number is associated with this point. Then we move the circle here. Same thing, repeat the procedure, we get a point, a value for v. So we get a value for each point on this raster, and then we visualize it. We actually fit a surface to the raster, or turn it into a pixel image or something like that. And that is the point. In 2 dimensions, you can actually see it. You know, you would have, let's say these are our points. And in 2 dimensions, we would have our pegs in regular intervals. At each of these, we would take our function, compute the value, and then for each of these, we have a value, and then we put it together, and we end up with a You can think of the same thing here. You can think of these as being spikes sticking out. And then you fit a surface to the spikes in order to visualize it. So conceptually, it's a continuous function. But continuous functions, you can write them out. But